And we're back. Now we're going to do erosion caused by the wind. Oh my gosh, Doppler effect. Listen. Well, you didn't really hear it. Just got less loud. In any event, wind erosion. Wind blowing fast enough can pick up particles or sediment. Can pick up the particles of sediment. The two ways that we say that wind erodes is by deflation, which is simply picking up a particle off the ground and carrying it away, and by abrasion. That particle in the air hits another rock and breaks off a piece of that rock, blows it away, erodes it away. So, deflation and abrasion. Deflation, carrying away of smaller particles by the wind. Abrasion, wearing away of a rock by wind-driven particles. Wind carries away bits of the rock. Here you have abrasion. So, this pile of rock was part of a continuous sequence of layers sitting on top of this much more resistant sedimentary rock. And these are both sedimentary rocks, probably both sandstone. You can see individual layers where sand was deposited in some kind of setting. This layering is slightly tilted, probably after the sediment was deposited, after the rock had formed. And the wind has already eroded, and perhaps water in another climate had already eroded large portions of this layer that sits upon this rock. And what was left here is slowly being abraded. Particles that have been picked up by deflation, particles that are minerals, typically, maybe quartz, which is a hard mineral, strike this rock and slowly erode it away. That is abrasion. Here we see the particles in the air in a big dust storm. This is actually a dust storm that occurred early in the great American invasion of Iraq, as President Bush used to say. And of course, that invasion was in its early days, we can see, because they hadn't yet painted all these trucks that desert color. And we see this huge sandstorm or dust storm, because no doubt it's carrying particles that are the size of sand, silt, and clay. And those will be carried and deposited somewhere. So this is erosion by deflation, lifting the sediment off the ground. But also, these particles, if moving fast enough and if they are the right mineralogy, can erode rock that they hit as they travel at speed through the air. And here you could see exactly the kind of storm that might have been happening here in Iraq. This section up here, which is getting close to what is now considered, I think, parts of Kurdistan in Iraq, and maybe Mosul is up here, I think. And then here you have Syria, and then you got Lebanon and Israel, the West Bank, Gaza Strip, Sinai, Nile Delta, and where's Jordan? Jordan must be here. That's Jordan, and then Saudi Arabia. So Jordan, Syria, Lebanon, Israel, the famous Golan Heights next to Syria, which is actually Syrian territory taken by Israel, and Syrians have not ever made some kind of deal to get it back. And the West Bank, of course, which was not part of Israel as it was founded in 1948, but which was won in the 1967 war by, or occupied by, Israel after the 67 war. In that same war, Israel occupied the Sinai, but then negotiated a give back in 1979. And of course, as of just today, we have terrible fighting breaking out over the attempt to take over property of Palestinians in East Jerusalem, and then the response from Palestinians in Gaza firing rockets into Israel, now Israel fighting back. So, terrible situation which never seems to be resolved. And of course, Turkey's up here, and Turkey has a big interest in this region as well. So, dust storms and political storms. So what happens? Well, the wind is blowing. If it's not blowing too hard, the particles of sediment that are impacted by the wind will creep across the surface. If it's blowing hard enough, they are said to saltate across. They are lifted up and they blow, and then they can hit another rock and abrade it. If they collide with a second particle in the air, it's called attrition, because the particles are broken up into smaller particles. And as we see in the dust storm, some of the particles, probably the size of clay and silt, can be suspended, mostly clay, and blown hundreds of miles over the surface of the earth, where they can be deposited as what is called loess, which is a type of deposited sediment deposited by the wind, and makes very good foundation for agriculture land. And we'll talk about that when we talk about deposition. So, what's the consequence of this wind erosion? Well, we get deflation, 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 and what you notice that the larger particles don't get moved, but the smaller ones, the sand, silt, and clay, get blown away until the larger ones begin to accumulate, and you get what's called desert pavement, which would look like this, where in between the larger particles there are still small sand, silt, clay that can be blown, but there's less and less of it as every windstorm deflates these smaller particles away. And then you're left with these larger ones. And you can see, actually, it's really quite interesting to see what's left behind, because some of this actually looks like basalt. So it looks very volcanic to me. And likewise, it's very angular, which means it hasn't had tremendous amount of time to be abraded either by the wind, and it wasn't in a water environment where it might have been abraded and rounded. That takes us to erosion by glaciers, which is the last type of erosion we'll talk about. A glacier is a river, or you could even call it an ocean of ice, depending on the type of glacier. We have two types of glaciers. We have an alpine, also called valley glacier. These form at high elevation and tend to form moving down from the tops of the mountains to lower elevation, as long as it's cold enough to maintain a front which is not melting faster than it's growing. It moves like a river downhill, but very slowly, obviously. Then you have your continental glaciers, which moves over a large area from a spreading center of accumulating snowfall. So in both cases, you can say that the glaciers are formed by accumulating snowfall. So up at the top of the mountain, the snow falls and doesn't melt in the summer, keeps accumulating, and pushing that river of snow, which then becomes compacted ice down the mountain. Continental glacier, the same idea, accumulating snow, which then becomes so heavy, there's so much pressure pushing down that it spreads out in all directions from a center. Alpine glaciers develop then at high altitude. They follow valleys occupied by streams. They're narrow and long, and they flow downhill. Continental glaciers develop at high latitudes. They're very large, and they flow out from the center in all directions. Glacial movement is by plastic flow. So plastic meaning that it's not a liquid, except perhaps a little bit based on pressure might form at the bottom of the glacier. The pressure might change some of the ice into liquid. But what you can see is if you have the original line of stakes where the glacier first began to move, there's a slow descent of the accumulated snow. Again, what happens is there's so much snow up here that it can't build up any longer, and it pushes down and begins to squeeze itself down the mountain. Now, there's enough snow. If there is enough snow, it has enough force to begin to grind up the rock that's underneath it, and you get some characteristic landscape forms based on that. So accumulated snow compacts into a thick layer of ice that flows downhill if alpine, moving laterally over the land if continental. Alpine glaciers flow down as snow accumulates at high elevation. As long as temperature allows the lowest elevation snow/ice to melt at a rate slower than the snow is accumulating, the glacier will grow. So if you get more accumulation, more accumulation, more accumulation, then you have melt, 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 you get growth, growth, growth. As soon as you have more melting than accumulation, well, then the glacier begins to retreat back up the mountain. Here's a beautiful picture of some alpine and valley glaciers that have been growing out of this source area. So here's where the snow is accumulating and then pushing its way down the mountain, picking up sediment. Why you see this snow is so gray is that it's grinding down the rock underneath it and picking up sediment as it goes. In fact, seasonally it will melt back towards the center and leave a line of what's called moraine. You have lateral moraine here, and you have moraine in the middle where the glacier carries vast amounts of sediment down the mountain from every size, from clay to silt to sand to pebbles and cobbles and boulders can be carried by the glacier. Here's a continental glacier where the snow accumulates at the top, and what we have here as an example would be the bedrock under, say, Antarctica today, or the bedrock under Greenland. Now, in the case of Greenland, you still have annual snowfall. Antarctica is essentially like a desert. There's not a lot of annual snowfall. Most of the snow that moves that you might see in a movie about Antarctica is wind-blown snow. It's more like the desert with a dust storm. Instead, it's lifted up or deflated snow that gets lifted up and blown around. But in this case, the formation would be that you started with an annual deposition of snow that doesn't melt in the summer and slowly builds up, builds up, builds up, builds up, builds up, and then at a certain point there's enough mass that it's beginning to push down and flowing laterally out, grinding up the earth underneath it, and then when it reaches the ocean in Greenland, calving icebergs. And in Antarctica, we have an ice shelf, which also calves icebergs. That's what they call it. It's like making a baby, a calf. Why are glaciers then agents of erosion? Well, they weather rock by frost action, freezing, thawing, freezing, thawing, freezing, thawing, break, abrasion, grind, 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 plucking, picking up, and moving. So in all these ways, they move rock, split, fall, abrade, move, pluck, carry. They move huge amounts of sediments, long distances. All sizes become part of the glacier. Alpine valley or valley glaciers, erosional features. You have a shape called a cirque, a bowl-shaped area at the top of a valley glacier where the glacier has formed. You have the arête, a thin knife-like ridge between glacial valleys. Arête is a fishbone in French. So this thin little bone of rock that sticks up and separates two areas where a glacier may have formed. And you have the horn, a pointed peak carved out on all sides over a long period of time by the abrasion, the force of abrasion that a glacier can apply to rock. So here's your cirque with a glacier in it. Potentially, if this was surrounded on all sides by other glaciers, this could become a horn. The arête is this edge here. The arête is the edge of the cirque in this case. Oh, I don't want that. What are you doing? Give me a break. Here's your arête, your knife-like edge, and down here would be a cirque, and this area has all been carved out by permanent ice, the form of a glacier. Here's again an arête, a long arête with some cirques that no longer have glacial ice in them because either it's melted, well, it's melted away. So all of this would have been cirque-like. And then your horn. This could be the Matterhorn in Switzerland, which has been formed by the erosion of the rock by glacier that covered the mountain at some point in the past, geologic past. Now, glaciers are famous for producing, unlike a stream, which we dealt with in an earlier erosion video, they don't make V-shaped valleys, they make U-shaped valleys. This beautiful U-shaped valley, which was once filled with a glacier. So what happens? Well, the glacier grinds its way through in this shape because of the way in which the snow is accumulated within the two walls of, say, these arêtes, right? And it grinds out, freezing, thawing, plucking, abrading, and carves over time these beautiful, beautiful U-shaped valleys. Here we can see some beautiful glaciers from Alaska, where you can see they really are rivers of ice. Here's the source, and then the glaciers moving down elevation, and you can see within the glacier that's flowing out this grayness, because that's the sediment that's been picked up by the ice as it slowly grinds its way down the valley. Here's another glacier moving into the water directly. This may be in retreat. But again, you don't see as much sediment with this. But I wouldn't be surprised if this is a retreating glacier. Now, one of the things that allows you to see the effects of erosion, even in New York, is that often the material that's been picked up, the rocks that have been picked up in the size of boulders and cobbles and even pebbles, can grind the bedrock below. And we see this in Manhattan. It says here, grooves and striations are carved into the bedrock by pebbles and cobbles carried away by the glacier. The grooves indicate the direction of glacial flow. And here we see a good example of that. So we see these grooves here, which are the result of a glacier grinding across this bedrock. Now, this bedrock is somewhere probably in the United States, but I'm not sure where. But a really great example for you guys is right downtown, just north of 59th Street, Hexter Playground, I think. So if you live down there, they're these big rocks. We're looking from the northwest to the southeast. This is that big, giant new apartment building that sways and creaks and leaks. But these are grooves created by rock, grinding rock, and then water probably flowing over this, adding to it. And this is the result of the glacier having grown to the southwest and grown to the southeast and retreated to the northwest. So I am looking southeast. The glacier got bigger and bigger and bigger, and then in time, 18,000 years ago, started to melt back. Here you see just to a little bit further, there's a long groove here where, again, rock being carried either down, imagine a rock like this. This is a heavy piece of granite. Imagine a rock like this stuck in the ice and just grinding its way through the bedrock. And not in 5 minutes. I'm talking about, it could be down there grinding for a year, 2 years, very slow and very, very decisive. Here we go, some more beautiful signs of past glacial activity in Manhattan. And this is the last slide I'm going to show here, and I'm going to go to this link, and I may freeze when I talk, and if I do, well, just listen on. We're going to just look at how the glaciers of Greenland have been shrinking. And it says here at least 200 of the island's coastal glaciers have retreated over the past 20 years. And one of the things you may remember is that we are looking at the NASA Earth Observatory. Remember? We used this in the fall. And we had to tell us what the image was. And remember, these are the instruments, the Landsat 7 and the Landsat 8, which you might remember were very good at getting certain types of information by electromagnetic energy. And it's significant that the glaciers are retreating. So we go back to where we began. As we end the year looking at glaciers, we go back to the tools that we learned of in the fall. So hope you can find the time in the future to enjoy the NASA's observatory and maybe even look at other images. So for instance, here's a nice image from 2012, winter and summer in a part of Canada called Bilot Island. Here's the winter, here's the summer, here's the winter, here's the summer. And then we had the instrument Terra using the MODIS, I can't remember which MODIS was, the moderate resolution imaging spectroradiometer. So maybe it uses, well, maybe let's take a look. What does it use? True color image, Lake Winnipeg at Lake Winnipegosis, Manitoba. I don't know more for the moment, but I think that's where we'll stop.